Thanks a lot for the kind introduction, Unity-san, and also thanks a lot for the kind invitation to this fascinating symposium by the organizer. So as just introduced by Unity-san, I'm a senior scientist and also currently the innovation lead in the material science and the chemistry department of Institute of High Performance Computing, A*STAR. So today I would like to introduce our work on the quantum computing research in IHPC. And to be frank, we are quite new in the field. And I would say that most of the people here might be our sensing, to my most of the understanding. I think we are here more to learn and to share what we have gained from the last 2 to 3 years of efforts. So starting from the starting from the outline of this talk, I would like to introduce IHPC and A*STAR, and also then I will look slightly deeper into the quantum research in Singapore and A*STAR. So I believe the Professor Latoria in the morning have done a quite good introduction to some of the research there, but I will give a slightly more introduction to some other activities in Singapore. Then I will introduce to our quantum computing research in IHPC with a focusing on 4 areas. One is the many-body physics in quantum chemistry, material and quantum optics. The second one is quantum-inspired optimization. And the third one is quantum algorithms, quantum complexity, and quantum error mitigation. And the last one is the full-stack software platform for quantum computing. So as I believe the Sato-san in the morning also have a very good introduction towards some of the efforts that he has made in R-CCS. Now moving to the introduction to A*STAR, so who we are. So we are actually we have a very similar structure to maybe some of the national labs in US, such as Oak Ridge, as introduced by Travis Humboldt in the morning. And also has some similar structure to reckon. So in A*STAR, we are looking at the advanced science and develop innovation technology to further economic growth and improve lives. So last year was our 30th anniversary, and IHPC is slightly younger than A*STAR. So we established on 1998, and currently we have somewhere around 400 researchers, with most of them are PhDs, and all of the researchers are working in a multidisciplinary manner under one roof. So we also publish quite a bit of annually, and we also have quite strong collaboration with various industry and government agencies. So we are here to look into the modeling and simulation and AI. And we are looking at the system from molecules to large-scale systems. And we also have digitalization of representation of physical things. And here we are trying to incorporate physics, chemistry, and human behavior, etc. So that it is accurate. And from digital representation can do many things and to understand why, and which allows us to design better and optimize. And then with all this knowledge in the modeling, we can detect and predict to help the leveraging, to help the upgrading and developments in the industry field. So as in a knowledge-driven economy, we need to move up the value chain and also design and innovate products. So we do have lots of projects in the design and new products, services, and yield significant values for the companies and the public agencies. So here is the overview of the departments that we have in IHPC. We have now we have 7 departments and 6 cross-departmental initiatives looking at various aspects of modeling and simulation and AI. And now we are, of course, moving into quantum as well. So maybe will become one of the, for example, cross-departmental initiative in the future. So now let me go to the landscape view of quantum research in Singapore. But I would say that the contents here might not be might not be inclusive of might not be extensive. So we are here. So we are looking at the quantum sensor, photonics, quantum materials, solid state qubits, and well, traditionally we are good at HPC modeling and simulation AI. Now moving to the quantum field, we are looking at the quantum algorithms, especially the applied one, and looking at software development, and also development of applications. So we also have large groups, especially centered around the Center for Quantum Technology, Center for Quantum Technology in the US. They are looking at the various aspects of quantum technologies, and has been there for almost 15 years. And we also have two major universities like the Nanyang Technological University, which I obtained my PhD degree from, working on the things like quantum materials, quantum photonics, hybrid quantum system, quantum engineering, and also SUTD working on other aspects, or the many aspects of quantum theory and also quantum optics. So we have a research community where you can find the detailed information on the quantum community through this quantum SG. And we have a few startups such as the Horizon Quantum Computing. So probably some of you have heard of it, and Entropical Labs, etc. So in A-star, we are looking at the 4 major domains in quantum research. So we are looking at the practical devices for quantum communication and biomedical and manufacturing in the sensor field. We're also looking at the new scalable and robust qubit platform, as well as cryogenic electronics. We are also looking at the traceable calibration and fundamental standards from the angle of quantum metrology. So for us, we are specifically looking at how to expand our HPC domain expertise to quantum computing via the innovation in algorithm and the software developments. So we are also part of this major national level initiative, which is called the National Quantum Computing Hub. Although the official announcement of this hub might comes in soon. So we are part of the many of the developments, such as the classical simulator, algorithm, the applied algorithm, as well as applications, and also to engage and interfacing with industry. We're also looking at the developments of full stack, open source middleware, and also the backends based on the actually hardware, HPC, and also potentially cloud, various kinds of cloud access to different computing service providers. So, of course, we have quite extensive international collaborations where we are working closely with R-CCS, and hopefully we can find the opportunity to extend the collaboration further with RQC. And we also have established collaboration with Barcelona Superconducting Center, TII, University of Milan, and more through for example, the collaboration in the developments of cable. So for IHPC, we are looking at achieving practical quantum advantage by innovating end-to-end hardware agnostic full stack quantum accelerator solution that leverages the translation of IHPC's expertise and strengths in modeling and simulations and AI, and hopefully our efforts would enable us to serve better for the quantum ecosystem. So apparently why we are interested in quantum computing, so that is quite apparent. So we are looking at to harness the potential exponential acceleration for economic important applications. So by doing so, how we are going to do so? We are looking at how to leverage on our domain expertise and also our quantitative talents who have knowledge in both the quantum chemistry, quantum many-body systems, and more, and HPC as well. So we are also looking at the ability. We are also having the ability to compare and combine with classical computing, and we also have good access to a startup network of industry partners. So from here, you can see that we are positioning ourselves not really at the very basic level, but also at the translation level that connects to the industry as well as public agencies. So our strategy towards developing our quantum computing capabilities for algorithms, software, and applications are the following. So we are looking at the problem at the occurrences that the practical quantum algorithms cannot really be run on the current quantum hardware devices, and also there is a strong demand and also shortage on the quantum computing talents. So we will like to leverage on the development of talents, and also in order to do so, we want to have something to leverage on. So that is developing this platform. So this platform is the one that we would like to leverage on, so that we can translate our experiences for real-world modeling and simulation and AI to the quantum domain. And the overall goal is to develop this use case-driven quantum algorithm software and applications by leveraging the development of this platform. So in this platform, we have three major components. One is the two are at the relatively higher level, or more application level, relevant to the simulation, both the simulation for quantum chemistry, quantum materials, and quantum optics, and also large-scale simulations in, for example, computational fluid dynamics and also computational electromagnetism. We're also looking at the optimization problems. We are looking at optimization for logistic, operational research, warehouse management, manufacturing, and also AI as well. But we also devise a strategy to look into the software for the control and readout. So, okay, at currently, we don't really touch anything on hardware, but we would like to leverage on all the developments for algorithm, software, and applications to harness the power of the NISQ devices as much as possible. Now, let me move to example on how we would like to develop this end-to-end full-stack workflow. So we start with a certain type of problem. So we always has to define the problem. So for this one, I take this quadratic assignment problem in warehouse management as an example. So starting from the end user engagement, we understand the needs from the users, and then we formulate the problem together with them. And then we have to translate the problem, like this pictorial problem, into a certain mathematical form, like this cross function. Then how we are going to do to solve it on quantum computing? We would like to look into how to divide this problem into the one that is relatively potentially easy for quantum computers, and also there are also large parts of the problem that are classical, easy, or feasible. And for the quantum easy or quantum feasible ones, we are looking at what are the proper quantum algorithms that can be solved. For example, let's say if we can use this QAOA algorithm to solve for the optimization problem, or we can also try to use the quantum annealing to solve for this problem. And another very interesting part of the problem is about the physical nature, because apparently if we are mapping it to some models such as QUBO, we are able to look into the things like symmetry of the problem, and also that will also help us to look into how can we better improve the design of our ANDAs or our quantum algorithms. Then we have to look into for example, how to map the problem into the different types of devices. So at current stage, we also regard the IHPC as one type of a backend that we can implement our problem on. Last but not least, we're looking at we are looking at the making sense of the problem, and by comparing the results of the different devices in solving for such a problem, and then we can see, okay, which device might be more suitable for which kind of problem, and then we can close loop for this workflow development and deploy it as a complete solution. So here are the introduction of all the major research domain in IHPC for quantum computing. So we are looking at as I just mentioned, we are looking at quantum simulations. We are also looking at using quantum computers to solve for linear systems and differential equations. For example, for this waveguide problem, as well as for this time-dependent heat transfer problems. and we are looking at the possibility of harnessing the power of quantum computers to solve for large-scale computational fluid dynamics problem for urban design, and also for AI model training. And we are also looking at the optimization as well as the quantum control and readout. And we also have fundamental horizontal building piece, horizontal piece of work looking at the quantum algorithms, development of quantum algorithms, quantum complexity, and quantum error mitigation, as well as software engineering. So today, as I just mentioned, I will quickly go through all the work that we have, some of the representative work that we have done for quantum simulation optimization, as well as some of the horizontal work in IHPC. So this is our team looking at the many-body quantum physics in quantum chemistry and materials and quantum optics. So for the quantum chemistry one, we consider the adoption of these quantum computers for classical information business quantum chemistry. So we attempted to use this ADKR model to communicate our transformation from classical to quantum. So in this field, we gradually building up our capabilities, starting from our awareness of the potential advantage of quantum computers. Since then, we established a collaboration with Dimitri's galactic groups in CQT, and currently building up a lot of the interesting work with them. So here is an example of our work. So we try to look into this benchmarking work to replicate. So first of all, we need to replicate the things done by the Google's team, and then the unitary of transformation of this one electron reduced tension matrix and two reduced tension matrix obtained from Hartree-Fock energy is starting for our own developments, such as optical optimization, etc. So recently we attempted to redesign the Hartree-Fock algorithm ANDATS based on the keyboard framework, and also we have tried to develop this MP2 ANDATS for BQE. But at current stage, the results are relatively preliminary. So please bear with me that I cannot show more than I from this slide. But hopefully I can show more in the future. So for materials, we are looking at the modern simulation of quantum materials, and looking at the potential to harness the potential exponential speed up through the quantum simulations, and to exploit NISQ devices, algorithms, as well as emerging quantum hardware to accelerate the simulation of materials, where the many-body quantum physics, especially the CJ, especially when correlations becomes important in the systems. So one of our objective in this field is that we are aiming to look into the benchmark to look of the quantum and the classical algorithms, and to look into for example, the Ising models, Heisenberg spin chain, impurity Hamiltonian, and all those. So I think the Yoneaki-san has done a quite good distribution and introduction to his work. So now let me move to some of the recent work that we have done for this the BQE ANDATS for long-range XY model. So in this work, we are specifically looking at specifically looking at how to design better ANDATS for solving this model. So we can the VQE feedback loop is sort of similar to anything else that you have seen. So I will not dive into the details. But specifically for this one, where we are trying to look into what things can be done here in the blue circle. We're trying to specifically look into the design of the ANDATS. So for this work, we are looking at the four types of ANDATS. Of course, the most obvious one is a mean field ANDATS, where we don't consider any entanglement, and it can be used as a baseline in order to compare with other type of ANDATS. And then we gradually design different types of ANDATS. Now here are the three types of them, but there are also variants. We have a full a fully entangled circuit and also a linear entangled circuit for each of them. Then we try to understand the behavior of the ondas in finding ground state energy solutions for this long range XY model. So in all these cases, we have fixed the J coupling to 1 and the number of sites to 4. But of course, we can increase the number of sites in a systematic manner, and it can potentially serve as one of the possible benchmarking problem. And then we are very h from minus to 2, and at current stage we haven't done the implementation of the algorithms on actual quantum hardware. So we are mainly leveraging on the simulator results. So starting with the relatively naive and almost straightforward design, which is a C-node, trying to introduce entanglements from C-node type of entangler. So where we don't see any, for this type of ondas, we don't see any variational parameters for the entangler. So we do see some slight improvements of our results, but we do also see that the overall ondas is not that expressive, even compared to the mean field. So at certain part of it, it seems to has slightly better results, but in the parts where the system become paramagnetic, we don't really see a lot of the improvements there. So now if we move to the second type of ondas, which is what we call the CRX, so control rotation X ondas, where we can introduce some degree of freedom for the rotate of these variational parameters into the entangler. We do see a lot of the improvements there, but as you can see, this ondas, even for the fully entangled ondas, we do see that the ondas is quite susceptible to sampling errors, and also we can see that the ondas is also poor expressive power. It also have poor expressive power for the new transition point. And then they further intrigued us to find out whether we can improve. We can further improve the ondas by introducing more variational parameters for the entangler. And actually, this TRQ ondas was inspired by the I-swap gate, and so that we are allowing the angles to vary. Then we can see that the overall performance of the ondas becomes much improved in terms of the overall value of the ground state energy as compared to the exact solution, and it becomes quite good in terms of the expressive power. So then we also investigated into this expressiveness of the ondas, and by comparing the VQ results against the exact solutions. So and for the site dependent for the chain length system side dependence, we can see that only these CRX and TRQ fully entangled ondas are able to capture the entanglement to the max extent. While we can also see that there is still some room to improve the ondas design, because we don't really want to have extremely deep circuit by having too many layers in order to make the sequence in order to make the system be entangled. So that we have investigated into how at which level we are able to reach the maximum entanglement for half-chain entanglement for this system, so that we will be able to reduce some of the efforts, some of the entanglement layers needed for the in order to reduce the computation resources required. Now moving to the quantum-inspired and as well as quantum-inspired optimization. So here is again is our team specifically looking into that direction. So I want to go into the details of the introduction. So we are trying to develop all the efforts from the top all the way to the level to the lowest level. So starting from the basics research, and we have the development all the way to the application and transfer research that is interfacing directly with various industry partners. So In this work, we look at how to we are looking at the cross-device benchmarking. We have 6 different types of backends, ranging all the way from quantum annealing to quantum-inspired devices and also classical devices. So we do see that we are trying to compare the quantum and the digital annealing and also the classical annealing methods, and we try to understand the advantage and the weak points of the various methods and to identify the challenges and the missing parts. Then for that one, we are looking at the constraints, problem size, and connectivity, etc. And the outcome is one of these efforts leads us to the fundamental guideline in choosing the appropriate devices for a specific type of application. So here are the 2 examples results showing that the D-Wave PAXAS is able to achieve faster solution for certain type of max card problem that we have extracted from publicly available repositories. And we can also see that even though the PAXAS can give very good results in terms of the quality of the solution, the PAXAS still can reach fairly good results as compared to the best classical solution solver. So then moving to the QAP problem. So this is something that I've shown for this workflow. So we can see that we are able to achieve the problem size of 19 items and 90 locations. But of course, there might be a possibility to extend the problem size further by considering, for example, the divide and conquer and the type of problem composition for optimization problems. Then moving to the time series forecasting, we actually worked with our industry collaborators, so specifically looking to look into the time series prediction and the forecasting using quantum annealing, and we do see that the overall results for this series of this hyper channel can gain quite an agreement with the classical methods, and also we do see some advantage of the quantum computers, at least not really surpassing, but at least it can get close results and also good accuracy as compared to the conventional simulated annealing results. And we also try to attempted to apply AI for hyperparameter tuning in order to squeeze more from the quantum devices. So here are some of the examples showing that we are able to use ML to achieve better results for the real-world data set. Then we are also developing into the QAA type of algorithms, and here are some of the recent efforts, but I will not go into the details due to the time constraint. Then moving to the quantum algorithm and the complexity, and also quantum algorithm team. So here are the team members. What we are looking at is we are focusing on 5 major areas. We are looking at the NISQ algorithms. We are also looking at the error mitigation techniques in order to reduce the errors for the from these algorithms. We are also looking at the building up. We are looking at building up the fundamental building blocks for optimization, quantum chemistry, and machine learning types of problems. We are also looking at finding the rigorous bound for the performance of the quantum algorithms. And we are looking at finding the proofs of these plausible evidence for the classical algorithms that cannot match the performance of the proposed quantum algorithm for the same problem. So which is serving the fundamentals of our benchmarking and the benchmarking targets. Then lastly but not least, we are trying to develop and have to look into have a deeper understanding of the power and the limitation of quantum computing. So here are some of the representative work, which I will not go into the details, but I will highlight our relatively recent work on the expectation estimation to reduce the measurements needed for various quantum algorithms. And we're also looking at the dependence of the performance of the quantum circuits with respect to circuit parameter and resources that is more relevant to the circuit optimization. And then we are looking at the performance of the variation algorithms for various types of applications. So the long-range XY and also the waveguide models of the ones that we have applied our method on. So here are some of the recent progress from us the error mitigation. So we are trying to devise good error mitigation strategy in order to reduce the error rate to reduce the error for the QAA type of algorithm. For at current stage, we are looking at the mascot, but we can be extended to other type of optimization problems. Last but not least, here is our group for the full stack software platform development for quantum computing. So here we are looking at the development of this full stack platform, starting all the way from applications to middleware that in direct connection with various type of backends, so that we are able to reduce the hurdles in implementing the quantum solution as much as possible. So finally, I'm reaching the end of my presentation. So I would like to thank all my team members for their great efforts, and also the funding support from A-Star. So we do have quite a bit of vacancies. So if there are people interested in joining us, please let me know. So yeah, with that, I end my talk here.